Hello, everyone, from the U.S. Fish and Wildlife Services National Conservation Training Center in Shepherdstown, West Virginia. My name is Ashley Fortune Isham, and I would like to welcome you to our webinar series that's held in partnership with the U.S. Geological Survey's National Climate Change and Wildlife Science Center, also known as NISQWSC. They're based out of Reston, Virginia. So the NISQWSC Climate Change Science and Management webinar series highlights their sponsored science projects related to climate change impacts and adaptation, aims to increase awareness and inform participants like you about potential and predicted climate change impacts on fish and wildlife. All right, without further ado, I'd like to welcome Emily Fort, Data and Information Coordinator from NISQWSC, to introduce today's speaker. Emily, welcome.
Thanks, Ashley, and thanks everyone for joining us. I'm happy to introduce Susan Dickerson-Lange. She's completing a PhD in Civil and Environmental Engineering at the University of Washington. Susan's dissertation research on snow processes and forested watersheds aims to inform land management decisions related to the timing of snowmelt and subsequent impacts on water supply, forest health, and stream ecology. This work has been supported in part by the Northwest Climate Science Center through the project Forest Management Tools to Maximize Snow Retention Under Climate Change. Susan is active in public outreach and collaboration with agencies and has utilized citizen science as part of her regional data collection efforts to observe snowmelt timing in different kinds of forests. With that, I'll turn it over to Susan. Thanks.
Excellent. Well, thanks again for joining us today. I'm Susan. I'm the picture right up there staring at you, and I wanted to start by conveying that this work has been strongly supported by an excellent group of collaborators from several different research institutions and by researchers and scientists who've been out in the mountains of the Pacific Northwest trying to understand forest effects on snow storage. So in terms of where we're going today, I'm going to start by motivating the question around how climate change and forest change might combine to affect snow storage and downstream resources. I'll give you some background on forest snow processes and talk a bit about our research on snow storage across the region, and specifically the Pacific Northwest region, and talk about a conceptual model that we've developed based on our observations across the Pacific Northwest as to what the key drivers are of snow storage, and then I'll conclude by leading you through an application of how to use a decision tree model to think about maximizing snow storage on the landscape. And just to give you a preview of my conclusions, all related to each of these sections, I hope to convince you today that the combined effects of climate change and forest change are important to consider together in terms of their impact on snow, and that forest snow processes vary in both time and space, which makes for a research challenge that is limited by a lack of observations of snow in forests, but that based on our work on the region, we see some key patterns allowing us to think about what the key drivers are, and that allows us to make some best estimates about actions for today and the future in terms of maximizing snow storage on the landscape. So starting with motivation, this is a generic hydrograph or a plot of stream flow through a single year starting in October and going through September for a watershed that receives both rain and snow as precipitation. This is a typical pattern where we see two peaks in the stream flow hydrograph, one in early winter or late fall, which is primarily driven by rain running off into the streams, and then one in the spring or summer driven by snow melt, where snow has been stored in the mountains and then melts off, becoming runoff in the streams. Now, there's been some great work looking at what the climate change effects might be on different basins and what they might be in general for these kinds of watersheds. And based on projections of warming temperatures, what we see is that in the stream flow we see a really clear signal of what's happening to the snow. That in particular, that based on warming temperatures we see less snow accumulating in these watersheds, so the spring peak declines, shifting some of that runoff to earlier in the year until we get to about the 2080s, where we see a lot more of our stream flow running off in the winter because that precipitation is falling as rain rather than as snow. Similarly, we see a key snowfall effect in a warming climate in the watersheds that are really dominated by snowfall as their precipitation, with, again, less snow accumulating and melting earlier, shifting that hydrograph earlier in the year. Now, we also know that forests have strong effects on the stream flow in a watershed, and both the magnitude and timing of stream flow. And forests are changing in concert with climate change, both due to forest management, like timber harvest, or silvicultural actions like thinning, as well as from prescribed fire and wildfire. So understanding how both of these things, climate change and forest change together, will affect water resources, or snow, is important for understanding future water resources. And this is not a new question. This is something that researchers and scientists have been looking at since the early 1900s. The Ouray Herald had a piece called "Does Timber Preserve Snow?" in a newspaper, trying to understand when the forest retains snow versus when the forest actually accelerates the disappearance of snow. And there's been some really interesting watershed scale studies done looking at different forest cutting patterns and how that affects snow and water stream flow. The challenge, however, is that the results lack transferability because these processes vary so much in time and space. Which brings me to a little bit of background about how forests modify individual snow processes. It's well understood that forests affect snow processes, and particularly through intercepting snow and reducing under canopy snowpack, as well as modifying melt rates through shading the snowpack from sunlight and sheltering the snowpack from wind. And that taken together, these have local effects like tree wells that you see if you're skiing or snowshoeing, as well as stand-scale effects in terms of the pattern and timing of snow disappearance across the forest stand. And that scales up to a watershed scale impact on snow storage as to the magnitude and duration of snow storage in the watershed, which has downstream implications for the timing and magnitude of stream flow, as well as stream temperature. Now, the research challenge, however, is that the individual forest snow processes vary in both magnitude and amount as well as direction. And so when combining all of the individual modifications of interception and melt processes, we can end up with two completely different cases. In one case, we can have snow storage where snow is persisting longer in forest gaps, like in the top photo, where the net effect of the forest is to actually accelerate snow disappearance. And we can have just as readily show a picture of the opposite effect where snow is retained within forests. So the net effect of the forest is to delay snow disappearance. So our research really revolves around trying to understand how these different processes combine to produce a net effect of whether snow storage will preferentially last longer in gaps or last longer in forest. Now, we started on this question by looking at a global analysis of all of the studies that we could find, and one of our key findings in analyzing these paired forest open studies was that mean winter temperature, so winter climate, is a key predictor of whether snow will last longer in the forest or whether snow will last longer in the open, giving us a sense of what the net effect of forest is on snow storage. In particular, in warmer winter climates, like right up here, like in the Pacific Northwest, or particularly the western Pacific Northwest of the USA, we see that snow lasts up to 2 weeks longer in open areas as compared to adjacent forests, whereas the opposite is true in colder winter climates, more continental climates like Colorado and Utah, where snow will last 2 weeks or more longer in the forest as compared to open areas. So this led us to take the next look and think about how snow storage varies across our own region. And we focused in on the Pacific Northwest for a few reasons. One is that it's heavily forested as well as heavily managed with lots of forest change happening. And we also see a strong climate gradient across the region, ranging from the warmer maritime climate west of the Cascades to a more continental climate east of the Cascades and into central Idaho, where we get up to we're down to fairly cold temperatures during the winter in the Sawtooth Mountains of central Idaho. And so we looked at trying to pull together as much data we could across the region to ask the question, how do forests and forest change affect the magnitude and duration of snow storage across the Pacific Northwest region, both today and in a warming climate? And we used actual snow observations from field studies at sites that included snow observations from open areas and adjacent forests, with ranging from dense forests, like the one that you see here in the bottom left, compared to this open area with sparse vegetation, to thinned forests, to forest gaps. And we looked at observations of snow depth through time at these paired sites, with particular emphasis on the magnitude and duration of snow storage, thinking about the peak snow ratio, the difference in snow between the open in blue and the forest in green, and the difference in snow duration, given by this metric of delta SDD, which is the difference in snow disappearance dates, giving us a metric for the duration of snow storage in the landscape. And what we found is that when we compared the peak snow ratio between open and forest at all of our sites across the region, and these are plotted here by mean winter temperature, that the ratio ranged from about 1 to all the way up to over 3. So at this site up here, we're looking at a ratio of almost 3 times as much snow in the open as compared to the forest. And this effect is really due to canopy snow interception for the most part, where in the open areas we don't have the trees intercepting the snow, where once the trees have intercepted and stored the snow, it's much more likely to be lost to the under canopy snowpack through melt or sublimation. In terms of comparing snow duration, what we found is that we saw both cases in the Pacific Northwest. In particular, at some sites, we saw a case where snow lasted up to about 5 weeks longer in the forest at these sites on the left-hand side of the plot, whereas at the rest of the sites, the difference in snow duration ranged from 0, so synchronous snow disappearance timing, to lasting more than 4 weeks longer in the open as compared to the forest. So we did quite a lot of process analysis around this, and we established that these patterns that we see in the snow duration plot down here are really driven by differences in snow accumulation between the forest and the open. And I'll get to that a bit here in a minute. I also want to point out there are certainly some limitations to this study in that there's a lot of interannual variability at these sites, where when we saw different data points from different years, considering this orange triangle, that it changes quite a bit from year to year. And we have substantial spatial data gaps, particularly on the eastern slopes of the Cascades and in central Idaho. But nonetheless, amongst the data set that we have, that we observe some clear patterns from which we can develop a best estimate as to the forest effects on snow storage across the region. And that brings me to our conceptual model of what the key drivers of snow storage are in the Pacific Northwest region. Because in trying to answer this question of how forests and forest change affect the magnitude and duration of snow storage across the region, we get into a predictive mode. So there's a few different approaches that we could use. Certainly we could use an empirical model approach based on observed data, or a distributed model approach where we use a physical hydrology model to try to understand the dynamics across the region. But both of these approaches are limited somewhat in a regional scale by the lack of forest snow data. In particular, although we have a network of snow observations across the region, they are almost all taken in open areas as compared to forests, with some exceptions with these research sites that you see here and a few others. And so we opted to develop a conceptual model based on process analysis from our results to try to make estimates about how forest-snow interactions might vary across the region and what that might mean for snow storage. So we find that the key drivers across the region, there's 2 key drivers. The first is that forest effects on snow accumulation, and the second is forest effects on snow ablation. Now, Forest effects on snow accumulation are what we see dominating the difference in snow storage between forests and open in the Pacific Northwest region. And in particular, I'm going to talk about canopy snow interception and wind effects on snow deposition. Forest effects on snow ablation, in terms of shading the snowpack from sunlight and sheltering the snowpack from wind, are also an effect, but are a secondary effect in the Pacific Northwest, where the sites that we're looking at are relatively warm. Now, this is where our analysis is really specific for the Pacific Northwest, where in a more continental climate like Colorado or Utah, we would likely see the forest effects on snow ablation rising to the top as a key driver, whereas it's really a secondary driver in this case. So starting with canopy snow interception and loss, is looking at the plot here of snow depth through time between the open, which is blue, and the forest, which is green, we see a clear signal of canopy snow interception, where we have more snow accumulating in the open. And that's because the trees, the needles, the stems, the branches, the trunks themselves are catching snow and storing it. Now, and in the Pacific Northwest, and specifically in the western Pacific Northwest, but across the region, we see a lot of canopy snow interception. And then once that snow is stored in the canopy, it melts, sublimates, or drops to the snowpack. So some of it rejoins the snowpack below the trees, and some of it is lost to the snowpack in the form of meltwater or sublimation. Now, one of the key reasons that this is such a driver in the Pacific Northwest is because we see more canopy snow interception in warmer climates. So in comparing continental climates, which are colder, to maritime climates, which are warmer, we see a much larger proportion of falling snow intercepted in maritime climates. And where the snow that is intercepted, then a large part of it actually will melt off. Up to about 70% of the snow that's stored in the canopy melts rather than just falling off and becoming part of the under canopy snowpack. Now, the controls on the magnitude of canopy snow interception, our temperature is a key control, because that's really determining how wet or sticky the snow is, which has a large effect on how much snow is intercepted by trees. Also, wind and relative humidity, other climate drivers, as well as storm sequences will affect the amount of canopy snow interception. And then lastly, forest structure will also affect the amount of canopy snow interception. And just as an aside, when we're thinking about canopy snow interception and the impact on snow storage, we've been doing some work in kind of diverse forest types where we've looked at different amounts of thinning versus gap cutting versus forest. And what we found specific to Western Washington is that there's a reduction in canopy snow interception when one cuts gaps or opens gaps in the forest, whereas we don't see a whole lot of reduction where we thin the forest. And that although we don't have a whole lot of data on this, we do think that from a thinning standpoint, we would need to reduce the forest to a minimum of less than 60% canopy cover, possibly more, to have any effect in terms of diminishing canopy snow interception in these forests. Okay, so canopy snow interception and loss is really driving the difference between snow storage at many of our sites across the Pacific Northwest. At a few of our sites, we see a different case, and these are the sites where we saw snow lasting longer in the forest as compared to the open. And what's happening at these sites are that we see wind-driven snow deposition, where the forest slows the wind speeds, resulting in deposition of snow within the forests. So we see this case where there's very little difference between snow depth between the open and the forest at this site. So at the same site, I'm going to give you two examples. The first is from the Cascade Crest in Oregon at one of our sites, where it's a topographically exposed ridge with high wind speeds. We're looking at hourly average wind speeds of up to 10 to 15 meters per second. As such, snow accumulation is more or less equal between the open and the forest through time due to the attenuation of winds in the forest and deposition of the winds within that forest. So really diminishing any difference between forest and open. The other place where we see this effect is one of our sites in the Palouse region of north central Idaho, given on this Idaho map in the inset right here. And we compared snow in this large open area at the blue dot to snow at this dense forest in the green dot, and found that more snow accumulated and lasted longer at the forest at this green dot. And this really points to, this is not a site that is topographically exposed like the first site. So the first one was a ridge site where it's a pass on a ridge, so it's getting a lot of wind for that reason. And in this case, this is in the Palouse region, which is known for high winds, particularly during storms. And we're also looking at an effect of the opening size and the fetch across the opening size here, resulting in high wind speeds and wind being a really dominant effect on differences between open and forest here. So in summary, I just talked about the effects of canopy snow interception and wind. And what we see is that when we look at this plot of the difference in snow storage duration, and we see the data points that are on this side of the plot where snow is lasting longer in the forest relative to the open are really driven by this wind-dominated environment where snow is being deposited in the forest and then protected from melting, which I'll get to in a moment. For all of the points on this side, this is where snow is either disappearing at the same time between the open and the forest, where they're close to this dotted line, or snow is lasting longer in the open. And this is really being set up by the difference between snow accumulation between the open and the forest due to canopy snow interception. Now, where they fall in this range is going to be a function of how much difference there is to start with between forest and open due to those accumulation effects, as well as how important the forest is for shading and affecting ablation or melt rates. So the key question when we start to think about forest effect on snow ablation or melt rates is really how much does the forest actually modify the ablation rates for a given location? Because that is going to depend on the conditions during the snow ablation season, and in particular will depend on how cloudy it is, as well as the solar elevation, which is a function of the time of year. I'm going to talk a little bit about each of these. First of all, the atmospheric conditions during the melt season really influence how important the forest is for shading. It's really a question of how cloudy is it during the melt season, because in a location where it's cloudy during the melt season, obviously the forest shading effect is not going to matter nearly as much for a location where it's sunny during the melt season. Now, this is a map of a mean cloudiness given as the average March, April, May atmospheric transmittance, so how much light can get through the atmosphere. And this is based on a model of temperature, but it's basically an approximation of how cloudy is it in the long term. And we can see distinct regional patterns with high cloudiness on the western side of the Cascades and the maritime Northwest, sunnier conditions in eastern Oregon and eastern Washington, followed by some moderately cloudy conditions in northern Idaho. Now, in terms of the time of year that we look and consider cloudiness, we also need to know when is the melt season, because that's going to vary locally as a function of elevation and region. So I'm giving you two examples here. We can get at this question with publicly available snow data from the NRCS SNOWTEL data network, of which the Northwest River Forecast Center interface is a really nice interface to get at this question of average snow disappearance timing. I'm showing two examples from that interface of a location here, Mount Gardner, which is on the western slopes of the Cascades, and Paradise, which is also in the western Cascades, but up on Mount Rainier. And what we can see is we can look at over the period of record, the minimum is in red, the average is in green, and the maximum is in blue. So this gives us a sense of when the average melt season is. So for Mount Gardner, which is just over 3,000 feet, if we look at this average melt curve, we can think about the ablation season as primarily being April and May, whereas at Paradise, which is over 5,000 feet, we can look at this average curve and think about how cloudy is it during May, June, and July, for example. The other reason we care about when the snow is melting for a given location is that the time of year is going to control what the solar elevation is. and that the solar elevation, which varies with time of year and latitude, is going to give us a sense of how important the forest is for shading. In particular, if we look earlier in the year, based on the tilt of the Earth's axis, in April, we're looking at lower amounts of solar radiation per unit area, lower amounts of sunlight, whereas closer to the solstice, we're looking at more. So depending on when the snow is melting will also depend on how much sunlight there is to shade from. Similarly, with the solar elevation also will affect how likely it is for the snow to be shaded by surrounding topography or for the forest, where the forest is likely to shade more area of the snowpack earlier in the year and less later in the year. Now, the whole reason for considering this is to really think about what is the relative importance of forest effects on shading the snow from sunlight. In particular, if we're in a regime where it's fairly cloudy during the melt season, regardless of when the snow is melting, the role of the forests in shading the snowpack is going to be minimal. Instead, if we're in a situation where the snow might be melting earlier or later in the year, but during sunny conditions, that forest shading effect is going to become an important secondary effect in determining the duration of snow storage and the difference between forest and open. And for locations where that shading effect is important, there become some extra complexities, which I'm not going to dwell on, but did want to mention that for locations where the forest shading is important, we start to think about things like topographic position and the effect on potential solar radiation. So the south side of Mount Rainier, for example, gets a lot more sun than the north side of Mount Rainier. We also start to think about black carbon effects from fire. Where there has been a fire, there's also soot deposition, which affects how much sunlight is actually absorbed by the snow and how much then contributes to melt. And we can also then think about forest gap geometry in terms of what size openings relative to the height of trees are going to affect shading. So then, with these drivers in mind, and particularly this kind of hierarchy of drivers that are determining how different snow storage is between open and forested areas, we can then use these to step through a decision tree framework to think about what kind of actions might support snow storage and maximizing snow storage under current and future conditions. Now, this is a beta version of our decision tree. This is available on our website. I'm going to show you in just a moment. But the key point is this. It's that what we do is we take the drivers and I'm putting them into a format where we can consider them one by one in what we think is the order of importance for determining the difference between forest and open snow storage. In particular, we start by considering wind effects on snow accumulation, because in windy sites, that's really going to dominate the difference between forest and open. The next set is really related to temperature effects on accumulation. Where temperature is higher, we're going to see more difference due to interception loss, whereas where temperature is colder, we'll see less difference due to interception loss. And then lastly, thinking about how important is the forest for shading the snowpack and stepping through whether there's cloudy or sunny conditions and what additional complexities that might add to thinking about the difference in snow storage between forests and open. Now, that decision tree that I just showed, as well as all of the maps that I've been showing, are available in beta versions right now on our website. That are publicly available as image files, as Google Earth files, and as a decision tree. This is still in progress, and we are also preparing a publication to describe all of this as well. And so at this point, are also still open to feedback as to how well these tools are working for folks. And my contact information is at the end. So I'm going to step through a few example cases based on our findings in terms of this hierarchy of effects and what that might mean for forest actions to maximize snow storage in the Pacific Northwest region. So starting with a high wind exposure case, for example, the crest of the Cascade Mountains in Washington and Oregon. In this case, because of the position on a topographic ridge, in many places wind effects will really dominate, in which case snow duration is likely to be longer in the forest relative to open areas. So if the goal is to maximize the duration of snow storage on the landscape, we would want to preserve the forests in those locations. Now, under a climate change scenario, we would also likely want to continue to preserve those forests. Now, granted, we don't know a whole lot about how wind fields might change as a result of climate change, that our projections aren't at that level, but that it's a safe bet that something that is exposed to high wind now will likely be exposed to high wind in the future, and that we might also consider thinning for forest resilience to make that forest more resilient to drought as well as to insect outbreak. The next case is the Western Cascades case, where on average we're looking at warm winter conditions and cloudy spring conditions, in which case canopy snow interception and then that subsequent loss really dominates the difference in snow storage between forest and open. The shading effect of the forest is minimized because of those cloudy spring conditions, and as a result, snow duration is fairly consistently longer in the open. So in terms of maximizing snow storage today, we would think about opening up the canopy. Now that could be in terms of gaps or thinning or harvest, but opening up the canopy to minimize that canopy snow interception effect, and that would be robust in the future as well. But that in the future, with warming temperatures, we'd also want to consider the rising elevation of the transition line between rain and snow, where warmer temperatures will lead to more rain and higher elevations. And so opening the canopy perhaps at higher elevations would lead to a longer-term effect on snow storage. Now, I want to pause there and point one thing out here, that with this framework, we're really thinking about average conditions, and I'm talking about average conditions. And so I'm bringing up this Mount Gardner snowtail plot again. And again, this is on the western slope of the Cascades. And we can look at average conditions for the period of record, which is that green line. And on average, it's a fairly cloudy spring. We see this fairly gradual decline in terms of the snowpack at that site, where we would normally expect in late May for there still to be a little bit of snow. Whereas on large snow years, we're going to have a quicker decline because the snow is melting later in the year. Now, water year 16 is really an anomaly, because water year 16, we have near normal amount of snowpack, but we have had an extraordinarily sunny late winter and spring conditions. And so as a result, although we had near normal snowpack, the snow melt rates have been very high. It's a very steep curve, and snow has already disappeared. In fact, it disappeared about a month ago at this site. So in this case, although I'm saying on average the shading effect is minimized in these conditions, for this year this would be an example of when that shading effect is definitely not minimized, that the shading effect would be important in this case. And so part of this framework is designed to be somewhat flexible to think about what are the conditions that perhaps are most important, that perhaps it's maximizing snow storage on an average basis. You know, for an average year, we'd want to maximize snow storage, but you could also step through this same kind of conceptual model thinking about maximizing snow storage on low snow years or high snow years, whatever the most important metric is to a particular question. Okay, the next case, we move to northern Idaho, where we have colder winter conditions, but we still have a fairly cloudy melt season in some locations. So in this case, we would see a situation where there's less interception as compared to the maritime western part of the region. So less interception because of the colder temperatures. And simultaneously, that shading effect is also minimized because it's a cloudy melt season. So as a result, snow duration is likely to be equal, where snow is disappearing at the forest and the open at the same time, ranging to somewhat longer in the open. So in terms of maximizing snow storage today, preserving the forest as is or opening the canopy are both likely to tend towards longer snow storage. And under changing climate with warmer temperatures, we might expect more canopy snow interception, that as those temperatures rise, we see stickier snow, and we see more on the lines of what we see on the western part of the region for interception rates. And so opening the canopy in that case would help snow storage potentially. The other piece of the puzzle, though, is that we don't know particularly how cloud conditions might change on average into the future. And so although we would expect that earlier in the season for it to stay probably as cloudy, that also could change. We really don't have good projections of cloudiness, for example. And then as a last case, moving to central Idaho, to the Sawtooth Mountains, where we're in a cold winter situation with a much more sunny melt season. And in this case, this is where we're getting closer to conditions that would be more typical of the continental U.S., the Colorado and Utah kind of conditions, where we see less of an interception effect, again, because of those colder winter temperatures. So that, first of all, sets us up so there's less difference between the forest and the open to start with. And subsequently, the shading effect of the forest becomes important for delaying snowmelt within the forest, which in this region leads to snow duration being more or less equal. So in today's climate, we would consider preserving the forest as is. In a changing climate where we might expect more interception, we could consider opening the canopy, but probably would want to lead towards north slopes with the idea of really making sure to continue to shade the snow as much as possible, but with the thought, too, that as temperatures warm, we might be looking at earlier snow ablation, which could be slightly different conditions, whereas snow is melting when it's sunny now. If the snow is melting earlier in the year, it's likely to be in slightly cloudier conditions, depending on the region that we're talking about. So to summarize, I hope that I've convinced you that thinking about the combined effects of climate change and forest change on snow is important, in particular because the timescales that we're dealing with for both are on the order of weeks. And so forest change has the potential to either mitigate or amplify the effect of climate change on snow storage and downstream resources. That forest snow processes vary substantially in time and space, which makes it difficult to talk about average conditions and capture all of the conditions that we see in a region, but that across the Pacific Northwest we are seeing these key patterns, which are leading us to conclude that forest effects on snow accumulation are really what's driving the difference in snow storage between forests and open. And in particular, windy conditions are resulting in snow lasting longer in the forest, whereas canopy snow interception, where there's low winds, that main effect is the canopy intercepting snow and resulting in a difference in snow between the forest and open, and snow lasting longer in the open. And that we can combine all of this to step through these drivers and think about actions for both today and the future in order to try to maximize snow storage based on how the forest is managed. With that, thank you. This is the website to get to any of those maps that I showed today, and I would be happy to answer questions.
Excellent presentation, Susan. Thank you very much. So we'll start with Bill's question. It says, in terms of canopy openings, does your research provide any guidance on size of openings in west side Cascades?
Sure, yeah. So a few things related to that. One is that on the west side of the Cascades is where we've done the most research on forest structure and snow, and we have found that openings rather than thinning is really where we see a difference in canopy snow interception. That said, the next two things that we would think about in terms of size of openings would be the solar geometry in terms of shading the snow and wind across the openings. From a solar geometry standpoint, because the west side of the Cascades tends to be so cloudy, it's less important. That said, 2016, we've seen it be really important. So on the west side, you could go one route and say, well, the size doesn't matter from a shading standpoint because it's cloudy. On the other side, there has been some really good research being done lately looking at solar geometry and the size of gaps, and what my colleague Keith Musselman has found is that right around 2 tree heights in diameter is where you start to lose the shading benefit of a gap. So that's for clear sky, sunny conditions. In terms of wind conditions across gaps, that is a big unknown. We really don't have a lot of data on wind effects in different size gaps. There's been some early research indicating that you can have wind effects within even a small gap of 1 tree height or right around 1 tree height or a little bit more. But that's an area of needed active research.
Excellent, thank you. And then we had some other questions, but for the east side as well.
Oh, great. This is Suzanne's question about same idea, but for the east side. So on the east side, well, first the caveat is that we don't actually have any forest snow data that I know of on the eastern slopes of the Cascades. It's a major spatial data gap that I know there's quite a few researchers trying to figure out how to get some data from there. So hopefully that will be coming in the next few years. But that being said, we would expect for shading to matter quite a lot more on the east side, where we see much sunnier conditions during the snowmelt season. And that's where the work being done modeling the solar geometry of gaps has really indicated that a gap you lose most of your shading effect once it's more than about 2 tree heights in diameter, depending, of course, on time of year and in terms of when the snow is melting. You can have a larger gap if your snow is melting earlier in the year and you need a smaller gap later in the year, as well as latitude.
Thank you, and I think you addressed Ryan's question in that response in terms of the snow dynamics in the East Cascades.
Sure, yeah, and actually I would add to that in terms of the East Cascades, like I said, it's a fairly big unknown, something that we don't have any data on, but I would be curious to know is what effect of like the Chinook winds coming through in the spring might also have on snow dynamics, where when you get large enough opening, you could get enough kind of turbulent heat flux where those winds are really driving melt and sublimation, that those kind of spring winds, late winter winds that come in may also have a large effect, but we don't know real well.
Thank you, and then jumping back up to Peter's question, it says, have you looked at the influence of dust on snow in the Pacific Northwest?
I haven't. There's been quite a bit of work done on dust on snow in Colorado in I believe the San Juan Mountains, and dust has a substantial effect of snow there, particularly because in much of that area is a regime where it's sunny during the melt season. So you add a little bit of dust on the snow and you are suddenly getting a lot more net solar radiation into the snow because the snow is less bright. And the albedo is lowered, it gets less bright, and therefore it reflects less of the sunlight. What we do see in the Pacific Northwest, I don't know about dust sources, which probably in the Palouse would make a difference, but I don't know of any work that's been done on that. There has been some work done in the Pacific Northwest, particularly in Oregon, on black carbon from wildfire, as well as I see Peter's question also relates to Montana. There's been some work done there as well. And both of those studies have found a substantial effect from the black carbon, soot deposition, the burned woody debris that results from wildfire, of increasing net solar radiation of up to about 300%, at least for a few years. So that's a situation where wildfire is going to open the canopy and reduce canopy snow interception losses. So you're opening the canopy and getting more snowed, but for at least a few years you'll have a substantial effect on the amount of solar radiation. So if it's in a sunny regime, that's going to continue to be a major effect. There hasn't been a definitive work on how long that effect lasts. The 2 studies that I know of that are referenced in this presentation, which will be archived, point to somewhere between at least 3 to 5 years, maybe more.
Thank you. And then same question for Idaho as well?
For Idaho as well, I would think it would be fairly similar. In northern Idaho, I know it's a slightly cloudier regime in general. It's somewhat cloudier, at least kind of based on the long-term averages, so perhaps would be less of a net effect. but would certainly in some years be a major effect.
Thank you. And then Bill asks, any tips for what to measure if doing a GOP influence study?
I'm guessing that's a gap influence study. I don't know what a GOP is, but so I'm going to go with a gap influence study. I mean, one is just looking at snow depth across the gap, really trying to get at the edge effects. There has been some work done really pointing to the importance of edges in certain places where, so in our work in the western part of Washington, the edges tend to be less important, and that really probably has a lot to do with the fact that shading is less important. As you get out to where I believe Bill is in Idaho, shading is going to be more important, and those actual edges are going to be more important for the kind of the net snow storage effect. So looking at what that variation is across a gap and across an edge would be important.
And then Suzanne asks, how about areas that have bug kill, such as the lodgepole pine, and in areas that have been burned?
Yeah, that's a great question. So there's been some work, some good work on like pine bark beetle effects, and certainly pine bark beetle as well as wildfire both reduce canopy snow interception. So you get a larger magnitude of peak snow storage in those areas. Where it gets a little tricky is in the effects of the forest during the melt season. That I've already spoken a little bit about burned forests where you have this black carbon effect, which will increase net solar radiation, at least in the short term. Similarly, with pine bark beetle, there's can be a similar effect from the deposition of the needles, kind of sloughing off, for lack of the precise term, in those locations. But I would think that that would be less of an effect than burned. But I don't know for sure, and I'm not sure if that's been assessed. But certainly, that would open up the canopy and affect canopy snow interception. The key thing is making sure that then the shading effects there aren't counteracting that.
Thank you. Jay asks, has there been any analysis of correlation between timing of snowmelt and how that manifests as streamflow? So does a 2-week delay in snowmelt equate to 2 weeks of higher streamflow? Or is it complicated by other variables reflecting soil saturation levels, groundwater recharge capacity, etc.?
Yes. So there actually has been some work done on this, and the relationships are remarkably stable. Now, a 2-week to 2-week would not be it would vary based on the location and the basin, right? But once you've kind of established that relationship in a particular watershed and in a particular gauge, those relationships actually are fairly stable through time. And Jay, if you want to get in touch with me, I can. Can't think of a citation right offhand, but there has been some work done on that you could look at in your own basin.
Bill asks another question. In steeper mountain slopes of the east side of the Cascades, we observe differential melt rates by elevation from valley bottom to the ridge tops on the southeast to the southwest slopes. So would shading effects vary by aspect and elevation combined?
I would think so. Let's see, elevationally from valley bottom to ridge tops on southeast and southwest slopes. Yes. So 2 things with that is that the elevation is really one of the things that's going to control when the snow is melting. And so as you're kind of going up in elevation, and typically as you go higher in elevation, your average disappearance timing is going to be later because you have more snow driven by orographic precipitation effects where you get higher precipitation at high elevations, and it's also colder. And so as you go higher in elevation, typically you would see more of an effect of aspect in terms of shading. So like the difference between a south and north-facing slope at higher elevation is likely to be larger than the difference between a north and south-facing slope at a lower elevation where the snow is melting earlier in the year when solar angles are lower, solar elevation is lower.
And then we have a question. I am sorry, I don't think I can pronounce your name. Zigbignu. Have you or anyone you know looked at the effects of multiple gaps, larger changes in the canopy boundary layer properties, and their relation to topographic effects such as shading, wind loading, and wind scour, or versus wind scour?
Oh, so thinking about kind of the compositive effects of a gap-dotted landscape. I don't think so. The best I would know of is I know in some of the Canadian groups near Banff are looking at landscapes that have lots of gaps in them because of the kind of the oil and gas industry is creating lots and lots of small-scale gaps in that landscape, but I am not sure. Point out again that our website link is on this last slide, and as well as my contact information. Like I said, that we're still kind of in beta mode with the decision tree model and some of these supporting spatial data sets, and so we're very much open to feedback or suggestions as we kind of put this together into a compiled format.
Suzanne just came in, so we'll go ahead and continue with her question. She writes that we have a large scale, or excuse me, we have a large salvage project in the works related to the lodgepole beetle kill. Can you direct me to articles that can address how big the gaps can be and what we need to keep in mind? So this is in an area where precipitation is low.
Yes. Yeah. So, well, Suzanne, I will follow up with you. I have your email address, and but I would point you to a paper that was recently put out in 2015 by Musselman et al. Doing the modeling on the relationship between gap size and time of year for clear sky conditions, which I think would be appropriate based on, I think that you're in Eastern Oregon. And then separately, I can direct you to some literature, doesn't come directly to mind, but on beetle kill and some of the hydrologic effects of beetle kill.
Thank you very much. So Kim also was asking the same question in regard to the Rio Grande Basin. Susan, I don't know if you want to take that.
Well, I think that would be real similar from the standpoint of, I think that the Rio Grande Basin is similar in that it's a fairly low precipitation, high, very sunny regime in the spring. But so I would suggest the same resources likely. Depending on, well, if Kim also wants to get in touch with me, I can suggest some more resources based on that situation.
All right, Emily, any closing remarks?
Oh, just big thank you to Susan. It was a great presentation, and we really appreciate her doing it and everyone's participation. So thanks again.
Excellent. Thank you, Emily. Excellent. Thank you, Susan, very much. Wonderful presentation. We had a lot of good discussion afterwards.
Great. Well, thank you for having me. I really appreciate it.